we need to talk about absolute entropy and the third law of thermodynamics and solve another problem. So you have an entropy balance for a reacting system. So here is the reactants flowing into the system, products, there's multiple reactants, multiple products flowing in and out, and you also have a heat transfer, Q dot, coming into the system, and it comes in and transfers across the boundary of the system, where the boundary of the system for entropy calculations, you have to know the temperature of the boundary of that system, because entropy is transferred with heat transfer. So if we look at our entropy balance, we're going to assume steady state, so no accumulation, depletion. We have heat transfer into the control volume with the heat transfer, entropy transfer with the heat transfer. So Q dot divided by TB. That gives us the rate of entropy transfer in with the heat transfer. The reactants are flowing in. So with the reactants, we get a flow in. Now we could put it on a mass basis, M dot S, and sum over all the reactants, but it's more common to put it on a molar basis, sum N dot S bar. So that's what's written here. So the molar flow rate of each of the reactants times its individual molar entropy. Then you have out, so we put a negative here. So it's the entropy flow with the products. Similarly, we'll put it on a mass, not a mass basis, but a molar flow rate basis. And then we have sigma dot. If there are any irreversibilities occurring in that chamber or that control volume, then that's like an in, it's a generation. That's why there's a plus right there. So that's what we have. The sum of in plus in minus out plus in is equal to 0. Hopefully all the signs make sense to you. So how do we calculate this entropy? And we have to deal with different reactions, and so it could be oxygen and then like O2, and then the oxygen could be bound up with carbon and CO2 or water, H2O. So you have to get everything on a common reference state. So people have thought about that and they've come up with an absolute entropy. So they calculate the entropy for an individual species I, let's say that's O2 or N2 or CO2 or something, as the entropy is a function of temperature only minus R bar and then a function of pressure, right? This natural log. That should look familiar to the other equations we had for entropy already in this class. So this is, let me just kind of go through it. It's entropy of a species on a molar basis as a function of temperature. That's not multiplying temperature, that's emphasizing this is a function of temperature only. And this naught, always a little confusing. What does that naught signify? At 1 atm pressure. It's our standard or reference pressure. Okay? And then this reference pressure right here is that 1 atm pressure. Okay, so now what is this P? That would be the pressure of the mixture, let's say the reactant mixture or the product, the mixture of the products or mixture of the reactants. So that's its total gas pressure times the mole fraction of that species in the mixture. So this is the partial pressure of whatever component we're talking about. If we're talking about CO2 or O2 or N2, those are very common. So every term you have to grapple with. What's R bar? That's an easy one. Ideal gas constant, 8.314, blah, 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 right? Okay, and so this entropy right here is a function of temperature and pressure. Or you might think of temperature, mole fraction of the species, and gas pressure. Okay, but it's a function of temperature and pressure. So the third law of thermodynamics helps us put everything on the same playing field. What they thought and they came up with is they said that absolute entropy of a pure crystalline structure or substance, is 0. It's set to 0. It's defined to be 0 at absolute 0 temperature. There's the starting point for all of these entropy measurements for all of the species. Another way to say it, the entropy of a pure crystalline structure at absolute Kelvin, 0 Kelvin, is equal to 0. It's the same thing, it's just reworded slightly differently. And one of the implications is it's impossible to get an absolute 0 entropy. So it's kind of an extrapolation to that point. Nothing ever gets there. There's no, like in a lab, somehow they're able to create a pure crystalline structure and have it at 0 Kelvin. Impossible. Okay? But they get stuff down to like 0.0001 Kelvin. The physicists do. They don't keep it there for very long, but they do get down there. So this is the third law of thermodynamics, and it's relating to the common entropy benchmark or measurement system. So just remember, pure crystalline structure, absolute 0 has absolute 0 entropy. So if we take a look at our table, we find the column labeled absolute entropy with our symbol S bar naught. And well, you said, hey, isn't that a function of temperature? Sure. It's everything in this table is at that temperature, 298 Kelvin. And so it's at 1 atm, that's that naught right there, superscript. So if you take a look, you'll find carbon dioxide in the gas form has this absolute entropy, oxygen in the gas form, that absolute entropy, etc. Notice the lowest value, it'll never get below 0, but it's close. It's carbon, solid, at 298. You keep cooling it, you get down to 0. But you'd have to take that carbon and not let it be amorphous, but let it be crystalline. What's carbon in a crystalline diamond? It's a diamond. Yes?
Why does carbon have a lower absolute entropy than hydrogen?
Well, one of the things is this is a solid. Okay. See the S? So that's like a chunk of coal. And the gases are more random and so if you want to think of physically, it's intuitive or helpful to think of entropy as randomness at the molecular level. Higher temperature, gases, much more random. Liquids, less random. Solids, less random. Amorphous solids, more random than crystalline solids at the molecular level. So low temperature crystalline solids, getting down there to 0 entropy because there's less disorder, less randomness.
So then would the third element have the lowest?
Which element?
It's right after helium.
Oh, nitrogen? No, where's helium? Oh, you're thinking periodic chart, like up there? Hydrogen, helium, lithium, beryllium. Some of them are liquid, some of them are at, these are at this temperature and pressure. So like you could have water in the liquid state. Notice how much lower the absolute entropy is than water in the vapor state, the gas state, at the same pressure and temperature. Right? Yeah. Okay. So we have now this column explained to us. It's for our absolute entropy. Notice how this table, A25, and this table, A23, are consistent. It's very important. So if we take a look at this absolute entropy, that was 298, 1 atm. Let's take a look at the value for oxygen. You go to the selected gas table, 298. Look at oxygen. Look at S bar. Notice that they even give you the name of it. It's the absolute entropy at 1 atm, right? They're telling you that's what S bar naught is. What is its value and how does it compare? Thankfully, they're consistent. Yeah, big thumbs up on that one. Let's take a look at water vapor. Water vapor's absolute entropy. Water vapor, absolute entropy, consistent. Let's do another one. Carbon monoxide. Carbon monoxide, see? Consistent. And then the last, carbon dioxide, for the ones that I show, carbon dioxide, they're consistent as well. That's great. So different molecules, everybody is on an absolute entropy scale. Okay? So you can calculate entropy with confidence. Let's solve this problem. We have a gaseous stream of pure methane. So here is CH4. And a stream of pure oxygen, O2, separate streams. And both of these streams are at 298 and 1 atm. 298, 1 atm. So this device has two bottles sitting there. One is a pure methane bottle and one is a pure oxygen bottle. And they feed this device. And it's coming into the device 298 Kelvin, 1 atm for both the streams. It's a fuel cell. Okay, well, what's a fuel cell do? It's a black box that's going to produce some power for us. Okay, you could read more about fuel cells, but it undergoes a chemical reaction inside such that streams of carbon dioxide, CO2, and a stream of H2O LiQ, liquid water, exit at what temperature? 298 Kelvin for the CO2 and 1 atm. At 298 Kelvin for the liquid water at 1 atm. Can you have liquid water exit at 1 atm? 298 Kelvin? Yes. Yeah, you can. It's possible. So that's a black box for a fuel cell. The fuel cell operates isothermally at 298. So anywhere around here, the surface TB is equal to 298 Kelvin. Okay. The surface of the black box called the fuel cell is 298 Kelvin. Determine the maximum theoretical work that the fuel cell can develop in kilojoules per kilomole of methane. So this fuel cell can produce some, what I'm going to say is W dot out of the control volume. And its form would be electrical, which is equivalent to mechanical. Okay, it carries with it no entropy, but it sure does carry with it energy. It's a power, mechanical or electrical power coming out of the fuel cell. And they want to know the maximum theoretical work in its per kilomole of methane. So what they want to know is W dot, maybe I put it up here, W dot out of the control volume, electric power, electric work, divided by N dot of the fuel. So if you have a dot dot, you need a dot dot there, right? So this is power over flow rate. Or WCV divided by N, where you get rid of the per unit time on both of them. This would be kilojoules per second divided by kilomole per second. You get rid of the seconds on both of them and you get the desired units, kilojoules per kilomole of fuel. True? Do we know what we were trying to calculate? Now the question is, how do I determine this maximum theoretical work? When you see maximum theoretical work, that's what goes off in your mind. What's going off in your mind is you're going to have to consider the second law of thermodynamics as well. And you're not going to have any irreversibilities. No irreversibilities. So sigma dot's 0. Sigma dot's 0. So does that mean I'm going to do this? Can I still have a Q dot for this fuel cell? They didn't rule anything out about Q dot for a fuel cell, and yes, it will be non-zero. So we need to consider that. You said we have a boundary temperature of 298, but that doesn't mean there's not a transfer of heat across that boundary temperature. Did it say anywhere that the fuel cell's adiabatic? If they would have said adiabatic, we would have said Q dot 0, hence no entropy transfer with the heat. But they didn't ever say that. And so what we have to do is we have to go slowly and we apply the first law. Once we have the first law of thermodynamics applied to this reacting system, then we can apply the second law to this reacting system. What's the equation for the first law look like? Okay, so we're going to have Q dot N, right, minus W dot CV out. I'm going to just get rid of this, just Q dot minus W dot CV, okay. We're going to do steady state, so it's, and then we're going to have, what else is an N? We have the sum of the molar flow rates times the molar enthalpies of all of the coming in reactants minus the sum of the products molar flow rate enthalpies. True? I like to go with ins and outs. Q dots in, W dots out. Sum of the reactants in, products out. So there's a minus sign in front of there. What we can do is write it this way. W dot CV minus Q dot, or put it like this. Q dot minus W dot CV is equal to the sum over the products of N H bar, and I'm going to put this over N dot fuel equal to N times H bar minus the sum over the reactants N H bar. All right, I'm trying to do a couple steps in algebra at the same time. Does that work for you? Good. So if we expand this, a product, well, we're going to have the, I guess I better write out my reaction equation. True? Combustion of methane with pure oxygen. So let's go ahead and tuck that in somewhere up here. CH4 plus some amount of O2 goes to CO2. How many CO2s? One. And then how many waters? H2Os. Count up the oxygen on that right-hand side. Finish it out. And we have no nitrogen to worry about. True? So that was good. So we have the stoichiometric coefficient for the CO2, which is 1, times enthalpy formation of CO2, plus delta H bar for the CO2. Well, the change in enthalpy from the reference state, it's coming out at 298. So isn't that 0? Isn't that 0? That's true. So let's continue with this equation. Plus, for the product, 2 times enthalpy of formation plus delta H bar. It's coming out at 0, so that's 0 as well. I mean, coming out at 298. But this is H2O-LiQ. It's liquid, liquid, liquid. It has a different enthalpy of formation than vapor. True? So be careful on that one. Minus, and then we're going to have 1 times the enthalpy formation for the methane, CH4, and the delta H. I should just get rid of all the delta H's because they're all 0. Everything comes in at 298 and goes out at 298. True? So let's dispense with that. Minus how many O2s? 2 enthalpy formation of O2 gas. So we have 3 gas streams, CO2, CH4, O2, 1 liquid stream, water, H2O. Now, at this point, I don't know what Q dot over N dot is. It could be non-zero. It probably is not equal to 0. And I'm really interested in this term, W dot CV over N dot F. That's the term I'm interested in. Isn't that what I want to compute? My answer? So really I have everything on the right-hand side of this equation is determinable. I go get the HF's enthalpy of formations. I get the whole right-hand side computed. But I have 2 unknowns on the left-hand side. I go to the second law of thermodynamics. For a reacting system, ooh, this is going to hurt, right? But it's steady state. And what do we have as an N? Q dot divided by TB. That's a 1 transfer in, right? The directions of both of these Q dots are consistent in the first law as well as in the second law, right? Then we're going to have an in with the reactants. So we're going to sum N dot, and then we'll put S bar naught for each of those reactants, minus the sum of N dot, S bar naught of each of the products, plus sigma dot. If we want the maximum, theoretical, my guess is sigma dot needs to be 0. It can't be negative. If it's positive, what you would do is you would actually find it. You would calculate that it reduces work or power. So we suspect that that's equal to 0 for a maximum. Okay? So let's expand this equation. I'm going to have to scroll down because there's just a lot to write. Is that okay? Yeah, let's go ahead and do that. So we're going to have the Q dot divided by N dot F divided by TB plus the sum of the coefficient S bar naught. And what I'm going to do is I'm going to say for the reactant CH4 plus N S bar naught for the reactant O2 minus N S bar naught for the product CO2 minus N S bar naught for the product H2O liquid. True? Did I get that right? All right. This is equal to 0. All right. So what you do is let me draw it. Let me just try and not do too much algebra here. But what is it? Q dot divided by N dot F divided by TB. Okay. What is the coefficient in front of CH4? 1. What is S bar naught for CH4? Well, it's going to be S bar naught at the temperature that it comes in at. The temperature that it comes in at is 298, isn't it? Minus R bar, natural log, the mole fraction of that stream that it comes in at, times the pressure of that stream that it comes in at, divided by 1 atm. That's our reference pressure. I stop, I pause. Does that look good? It's pure stream of CH4 methane coming in. So what's Y for that pure stream? What's the mole fraction of methane in a pure stream of methane? 1. And it's at 1 atm. So guess what? This is 1, this is 1, all that's 1. Natural log of 1 is 0. So this whole part goes to 0. So all you're left with is the value of the absolute entropy at 298, and I can get out of either, well, I get it out of the table. Okay. This is for the methane, CH4. You do the same thing for the oxygen. How many oxygens were there? 2. And then you'll have S bar naught of the oxygen at 298 minus R bar natural log of Y of the oxygen, pressure is a stream that the oxygen's coming in at, and then 1 atm for the reference. Same discussion. This is 1, this is 1, that's 1. Natural log of 1 is all 0. Boom. So you're just left with that one remaining term. So those are the two for the reactants. Let's take a look at the products. Minus CO2. How many CO2s? I have to scroll back up. I forgot myself. 1 CO2? Yes, and then 2 waters. So 1 CO2, S bar naught 298. And it's pure CO2 coming out. So even though there's a minus R bar natural log, that all goes to 0 for the CO2. Then we had 2 times the S bar naught at 298. Now, it's not coming out as a gas, all right? So this is where it's a liquid. That's where we end right there. Okay? We end right there for the liquid H2O LiQ. So we just get the value of S bar naught out of the table for H2O liquid. And it's in the table. Remember, it's right below the vapor. Should I jump back and see if I have that table? Let me see if I have that table. Okay, I have the gas, but right below it's the liquid. And there's an S bar. Maybe it's there it is. It's 69.95. Don't use the 188.72. There's a difference, true? That one's for the liquid, so that's the one we want. Okay. So at this point, take a look. Can I get this S, this S, this S, that S? Yes. Do we know TB? You know TB. And so you can actually calculate that ratio, Q dot over N dot F, to ensure that the second law is satisfied. True? So you can solve for Q dot over N dot F. The second thing you can do is go back now to the first law. And that first law is, this is now determined, right? So bring that over to the other side of the equation. You only have one unknown. You can solve for W dot over N dot F. That's our answer. That's what we wanted to do. Now you probably, I have to grab a bunch of numbers and put them in there, but let me show you a little bit of how I did this in Excel. All right. And so if you're looking for, let me just outline it for you. This right here is describing that methane coming into a fuel cell. And there's no nitrogens. There's no oxygen going out, but there is 2 H2Os going out, 1 CO2 going out for 1 methane and 2 oxygens coming in. So those are my N's. And I just recycling a previous spreadsheet. So I could change this, but this is, I usually do theoretical and then excess error. So that's why it's that doubled up. Now, coming in, we have methane, and I have to get enthalpy of formation, and I have to get S naught out of the tables for that methane. With the enthalpy of formation and the oxygen and everything, I can get the sum over all of the reactants of the coefficient times the enthalpy of formation. There's only really one term for the methane. That's in the energy. Likewise, CO2 going out, we type in its enthalpy of formation, and we know the stoichiometric coefficient, and there's no delta H. Delta H is 0, so we get the coefficient times H of F for the CO2. You do the same thing for H2O, but notice it's liquid. So I need to put in a liquid's enthalpy of formation, as well as over here I'm going to do entropy calculations in this zone. Right here I'm doing energy calculations. Okay? Whatever. Okay, let me escape here. So then I do the sum over all of the products for the energy. Okay. Now, let's take a look at the entropy calculations. I have to scoot a little bit here. We get the mole fractions of the methane coming in its own stream and the mole fraction of the oxygen coming in its own stream. And we have S naught and S naught. And so you can get N times S's, sum them up for all of the reactants. Likewise, the N times the S's, notice you need that S naught for the liquid water. You get the sum of the S's over all of the products, true? Okay, at this point I did it slightly differently, but we can definitely do it this way. Let me turn this around. What was our equation that we just developed?
2 times S naught over S naught. 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 2 times S naught over S naught
for calculating Q dot divided by N dot F. Wasn't that equal to the sum of the this one minus this one? I need to put a parenthesis there. And then we had to multiply by the 298 because the TB came up. True? And look at that. I did it slightly different, another way, but there I just did it, and they're consistent. Okay? So now I have the Q dot divided by N dot F. From the energy balance, the work minus the Q minus the work divided by NF is this. That just comes from this two difference. Okay? And so if I wanted to, I could calculate the work knowing that it's equal to minus this plus this. I just went back to the first law. Everything on the right-hand side was calculated, the sum of the products, sum of the reactants, and then brought over to Q, and so there it is. So that's our answer. So it's 818,023. All right. Now, what I had done earlier, though, was I had used a different technique, and I had calculated down here the term in the second law, Q dot over TB. So it's entropy transfer into the control volume with heat transfer for kilomole of fuel. You can see I explain it right there. The sum of the reactants right there. This is the sum of the products right there, just bringing it down. See that? Escape. Okay, and then what I had done was this is a sigma dot, and I would calculate the sigma dot from an entropy balance, and I didn't know necessarily what it would be, because I would guess this Q dot. Let me just look at this. Let me make sure. No, I would guess this one right here. Maybe I guessed it was 50,000. Okay, well, if it was 50,000, then my sigma dot's not 0. So in Excel, once you get used to Excel, you like the feature under Data. So under the Data tab, what if? Go to goal seek. I didn't name this thing. It should be like root finder or something like that. Okay, and it says take that cell, which is C25. I want to set it to make it go to a value of 0 by iteratively changing this one, and then there it is. So that's the way I did it originally, but you can do it a number of different ways. But you can see now, let's click OK. Let's say that somebody said, no, I think it's 900, 1, 2, 3, something like that. Well, you have a negative sigma dot. Impossible. Violates the second law of thermodynamics. Somebody says, no, I don't have that. I have whatever, 700. Well, you have a positive sigma dot, meaning there's some irreversibilities occurring. The maximum work you can get out of that fuel cell is 818,203. That's when sigma is equal to 0, right? So 818,023. And sigma dot's equal to 0. So it's reversible. Do you like or not like the Excel when I show it? Is it okay? It's okay? Okay. Sometimes I feel like it's not effective, but this is the end of the lecture. I have a little analogy to help you remember first, second, and third law of thermodynamics. It's not original to me. It's been out there for many years. Well, first law, second law, and third law are all about really energy, okay? And the first law says energy is conserved. Energy can be realized in different forms, It can be an internal, kinetic, potential energy, different forms of energy, chemical energy, but energy is conserved. It can be converted between forms, and as an engineer, we like to do that. We like to manipulate and convert energy between forms. But at the end of the day, the sum of the energy is constant. You didn't create any energy. You didn't destroy any energy. You just transferred it between forms as a clever engineer. True? The second law says there's a preferred direction for energy transfers. It's easy to convert work into heat. It's hard to convert heat into work. When they first did it, they thought it was impossible. If you want to lift something, get a muscle. Muscle on an animal or a muscle on a human. That's it. You don't burn something. A fire is to cook food. You're going to burn some wood and you're going to then pump water out of a mine? This is ridiculous. You're nuts. It's not going to happen. Heat engines were a major part of the Industrial Revolution, true? Burning something to turn something, burning something to lift something, do mechanical work. So we were going Q to work, which is hard. But the second law is there's a preferred direction in the transformation of energy. Third law, something about molecular motion in 0 Kelvin, saying that when you have something that's not at 0 Kelvin, it has molecular motion. And gases at high temperature have high molecular motion. And liquids at lower temperatures, less. Solids at lower temperature, less molecular motion. But you can't get below the absolute minimum where you have no molecular motion, 0 Kelvin, in a well-defined structure, a crystalline structure. Everything is well-defined in that case. And so that deals with the third law of thermodynamics. So what we do is we say, well, there's got to be an analogy over with energy. And energy, a lot of our lives are dealing with money. True? So the analogy goes between gambling, that's money, and money transfer. And it says, first law in gambling is money is conserved. At the beginning of the day, you have so much money. The house has so much money. You're gambling in Las Vegas against the house, right? And the money is there. At the end of the day, when you go to bed, the money's conserved. Either you won and the house lost, or you lost and the house won. True? But money didn't just trade and destroy. It's conserved. But what's the analogy with the second law? There's a preferred direction to the transfer of money. So that's the analogy that says, you know what? Either you win or the house wins. That's the first law. The second law is house always wins. That's the analogy there. It's a preferred direction in the transfer of money. And the third law is, unfortunately, you can't stop playing until you've reached absolute zero. So somebody else told me that a long time ago. And there's different variations of it, but there's your gambling analogy to the first, second, and third law of thermodynamics.